Okay, so last time we learned the other type of stereoisomerism, which is optical isomers, or we sometimes just call it enantiomers. So in order to find out whether a molecule can have enantiomers, we need to check whether we can find a chiral carbon. So a chiral carbon needs to be bonded to 4 different atoms or groups of atoms. Okay, and if you find that a molecule got a plane of symmetry, okay, so that's a key word you need to have when you're answering your questions. Okay, if you can find a plane of symmetry, then that molecule is for sure is achiral. Okay, and last time we went through some questions together, and here I left 2 questions with you. And today I'm going to teach you how to draw enantiomers and also how to work out whether, okay, the 2 molecules are identical or they are enantiomers. Okay? So, now take a look at question 4. So for this one, you can see we got 2 different molecules. So, how do we know, okay, whether they are identical or enantiomers? So first, I want you to start a new page, or you stay on that page while I turn to a new, okay, turn to a blank page to explain it. Okay, so for the first, sorry. Okay, so for the first one, we have this molecule. Okay, so there are 2 ways of drawing a enantiomer. So first, you can draw the mirror, and then by using the mirror, you can try to work out its enantiomer like this. Okay, so that's one of the way that to draw enantiomers. And then you will find out without the plane, actually, if you only choose the position of any 2, okay, if you change the position of any 2, and then you would be able to get an enantiomer of the original one. Okay, so other than changing the position of this ethyl group and hydroxyl group, okay, if you change the hydrogen with a methyl group, you actually get an enantiomer of this molecule. Okay, so by changing the position of 2 atoms or 2 groups of atoms, you get the enantiomer. Okay, and then if I change it once again, okay, so by doing this, I change the position once. If I change it twice, then I actually go back to the original one. Okay, so maybe here I change the position of the methyl group and hydrogen group. Okay, so now if I switch it once again, then I go back to the original molecule, because in the middle, that's the enantiomer. Okay, if I change it once, it becomes the enantiomer. If I go this way, that's the enantiomer. But these 2, they are identical molecules. Okay, so I want to show you the real model so you have a clear understanding of that. But give me a second. Okay, now that's one of the molecule. Okay, if that's my original molecule, okay, so if I switch the position of any two, okay, if I switch the position of the blue one and the purple one, I get the mirror image. Okay, did you see that? And then I take this molecule, as I have drawn, I switch the position of these two. Okay, so I do it twice. Okay, let me do this. Okay, now I switch the position of the red ball and the white ball. Okay, so I do it twice, then I get this new molecule. Now take a look. After rotated, that molecule is identical to the original one. Okay, did you see that? So if I switch the position twice or with an even number steps, I will get the original molecule. If I only do it with odd number step, I will change it into its enantiomer. Okay, so that's very important. Okay, so if I change the position once, I change the blue with the purple. Okay, I change the blue with purple. Now they are mirror image of each other. Okay, and switch once again. This time I try to switch the purple with red. Now I got this. Okay, and then you can see it go back to the original molecule. Okay, so by doing this, we can work out whether it's identical molecule or enantiomer. So if we go back to this molecule, so here, that's the beginning, okay? And then if I do it once, I get the enantiomer. That's this molecule. Okay, so now I want to see how many steps I need to go through in order to get the molecule on the right-hand side. Okay, so that's the first step. And then I need to get the hydrogen go to this position. So I will switch again, okay? So let me do it once more. So that's the second time I switch the position. I want to put my hydrogen to here. And then the OH group. Sorry, let me get back from erase them and start from the beginning. That's the original one. I change it once. I get this molecule. Okay, so because I go through odd number of steps, so that's the enantiomer of the original one, And then if I do the switching again, I want to get my OH group to this part, to here. Okay, so I'm going to switch the position of the methyl group and the OH group. So it will become OH here, methyl group here, and the ethyl group would stay at its original position. Okay, now I've gone through 2 steps, so it go back to the original molecules now. So that's the original molecule. And then I have to do one more step, okay? Because now the ethyl group and the methyl group are not at the right position of the molecules given in your question. So I have to do it again. Okay, so if I switch the position of the ethyl group with the methyl group, I will get this. Okay, so now I'm changing the original molecule to an enantiomer again. Okay, so this is a molecule given on the right hand side of that question. This is a molecule given on the right hand side of that question. So they are enantiomers. They are optical isomers. Okay, because it goes through 3 steps, odd number steps, so it becomes the enantiomer. So any questions so far? Or are you still with me? Hello? Okay, do you understand the first part? If you switch any position of the two groups, you get the enantiomer. Because when we take the mirror image, we actually just switch the position of any two. Or would it help if I show you the model again? Okay, let me show you the model again. Okay, so this is the original molecule. Okay, so by taking the mirror image, okay, if we have no, identical. Okay, so now I got 2 identical molecules. So if I take this one and switch any 2 of the balls, okay, for example, here I change the position of the white one with the red one, get this 2. Okay, so now and now they become enantiomers. So the new molecule is the mirror image of the first one, and no matter how I rotate it, they cannot overlap with each other. It's not superposable for this one. Okay, because I only switch the position of any 2 atoms once. But if I take this mirror image, okay, no matter which 2 I pick this time, maybe I pick the red one and blue one, okay, this 2, and switch the position. Okay, so I take this 2, left with the white one and purple one, stay on the same position. Okay, so that's a new molecule I get. And if I rotate it a little bit, you can see I go back to the original one. Okay, so when you take an even number steps, you actually go back to the original one. Okay, but if you take odd number step, you will change it into an enantiomer. It doesn't really matter which 2 you pick, okay, because you can just simply rotate the molecule. Okay, does that help? Okay, so if we go back to our drawing, so while approaching those questions, you just need to try, okay? How many times you need to switch those groups of atoms so that you can get the new molecule, okay? So for that question, question 4, this is a one given on the left. And now you want to, okay, by doing something, changing the position, you want to get this molecule, okay? And so then you need to switch it step by step. Okay, in one step, you can only switch the position of any two. Okay, so if I want to get the OH, maybe I get the hydrogen on top first. Okay, so I switch this two. And then I get the enantiomer. Okay, because I have gone through an odd step. Okay, so that's the enantiomer of the first one. Now we switch the OH with the methyl group here. So I'm taking the enantiomer of, or the mirror image of the second one. Okay, so I will go back to the original molecule. These two are identical. Okay, now if I compare this one with the final molecule, okay, we just need to switch the position of the methyl group and the ethyl group. Okay, so we need to do one more step. So we take the mirror image of this one, and then we get the enantiomer. Okay, so this is actually the enantiomer of the first molecule, of the original molecule. So we've gone through 3 steps. It's odd steps, odd number steps, okay? So if we're using the same method to attempt question 5, okay, we can try that again. For question 5, we begin with this molecule. Right? We begin with this molecule, and we want to approach the molecule on the right-hand side. Okay, so my first observation is that on the right-hand side, the molecule got bromine on top. Okay, so maybe I can switch the position of methyl group with bromine first. Okay, so let me do that. So now I want to have the bromine on top, and the rest, the COOH and the hydrogen would stay at its original position. So now I got my methyl group here. Okay, so I have gone through one step, so that's the enantiomer of the original one. But let's compare this one with the molecule you have on the right hand side. That's still a little bit different. The position of the hydrogen and methyl are different. Okay, so we need to go through one more step. So if I do it again, I will get this. Okay, so these two stay at the same position, but here I switch the position of the methyl group with hydrogen. Okay, so this one is a molecule given on the right hand side. And now you need to check. I have gone through 2 steps, so it's even number steps. So I have turned it back to the original molecule here. Okay, so for this one, you can choose, for question 5, you just need to choose D. They are identical molecules. Okay, so any question for 4 and 5 here, how to draw enantiomers? No, for odd steps, it will go to the enantiomer. For even steps, it will go to original, go back to original. Okay. So even step should be even number. Okay. Okay, now go back to the parts. So for question 4, they are enantiomers, and for question 5, they are identical. Okay. So the last part in this unit, we are going to talk about the properties of enantiomers, the chemical property and physical property. Okay, so for enantiomers, they have same chemical properties if they react with a chiral reactant. Okay, so later we're going to discuss in detail. But the other physical property is very important and is often tested in RFY exam. Okay, so for enantiomers, you need to know that they have same physical property, except that they rotate a beam of plane polarized light to the opposite direction. Okay, so please write with me. Okay, so what does it mean? If you take a look at this diagram, okay, if we have a source of polarized light and we got the samples in the tube, if we only have one enantiomer, okay, for example, if we only have this molecule in this tube, okay, then it would rotate the light to a certain degree and in one direction only, okay? Just for example, okay, if we put this molecule in the tube and it might rotate the light clockwise, let's say for 40 degrees, okay? So its enantiomer, which is this molecule, when we put this molecule in the tube, it will rotate the light in an opposite direction, so anti-clockwise, but with the same degree, 40 degree. Okay, so that's the different physical properties for enantiomers. If we put the same, okay, so they're gonna rotate the light to opposite direction, but with same degree. Okay, so we say a compound is optically active if it can rotate the plane of polarized light. So that means it can have enantiomers. Okay, so a compound is said to be optically active if it rotates the plane of polarized light. And for IFY, you don't need to bother what does it mean for a beam of polarized light. And also the principle of this is not assessed. And also whether it will rotate it clockwise or anti-clockwise, you don't need to worry about that. Okay, but you need to know that they can rotate it. And also the machine that we use to measure how much degree it rotates is called a polarimeter or polarimeter. Okay, both pronunciation can be found. Okay, so the name of that machine you need to remember. And if you want to know the detail, again, please scan the code I have attached. It got details explanation. Okay, as I have mentioned, if you only put a pure sample of one optical isomer in it, it will rotate it to one direction. So if we have a mixture that contains the same amount of the two enantiomer, okay, so if it are mixed with ratio 1 to 1, then we say they form a racemic mixture. Okay, so you need to remember this name. They form a racemic mixture because one of the enantiomer would turn it clockwise and the other one would turn it anti-clockwise. And they are in 1-to-1 ratio, so you will say the net rotation is 0. Okay, so net rotation of the plane polarized light is 0. It cancelled out. Okay, so for this part, you need to remember those terms. Okay, optically active polarimeter and also racemic mixture. These are important words. Okay, so let's move on. Here we got some checkpoint questions. Okay, let's attempt it together. So for the first one, compounds X1 and Z have the same molecular formula with structure as shown below. State the type of isomerism between X and Y. Okay, so if we take a look at X and Y, okay, first you can see they have the same functional group, okay? And then let's take a look at the position of the functional group. Okay, so the longest chain 1, 2, 3, 4, and for Y 1, 2, 3, 4. Okay, so it's not chain isomer, but the position of the OH group is different. Okay, so for the first one, it's attached at the end of the longest carbon chain. The second one in the middle of the carbon chain. Okay, so we describe X and Y, they are position isomer. Okay, and then how about Y and Z? Okay, so for Y, the longest chain 1, 2, 3, 4. But for Z, the longest chain 1, 2, 1, 2, 1, 2. Okay, so you can see they have the same functional group but different arrangement of the carbon chain. Okay, so we call them chain isomer. Okay, and the next part, one of the isomers exhibits optical isomerism, enantiomers. Draw the structure of the optical isomers. So let's take a look. Which one can have enantiomers? Remember, if we are going to find the chiral carbon, it must bind to four different groups of atoms. Okay, so take a look. Okay, the first one, we would not be able to find any carbon that have bonded to four different groups. For this carbon here, although it bonded to a propyl group and then a OH group, but it has two hydrogen attached to this. So it's not the chiral carbon. Okay, and for this one, for this molecule, for molecule Z, as you can see, the middle carbon, this carbon, bonded to 3 methyl group. That's the first methyl group, second methyl group, third methyl group. Okay, so this carbon here is not the chiral carbon. Okay, those carbon cannot be chiral carbon as well. It got 3 identical hydrogen attached to this carbon. Okay, so not possible. And then let's take a look at Y. Okay, which carbon on Y is the chiral carbon? Okay, it might be this one because this one bonded to, for now it bonded to 3 different groups. We have the OH group, we have the methyl group, we have the ethyl group, and you can see the final one, the remaining one should be a hydrogen here. Okay, so this one is actually the chiral carbon, so you can put a star to remind yourself. Okay, and then in order to draw the enantiomer, we need to turn it into a 3D representation. Okay, so we need to show its tetrahedral structure. So let's do it. So we put the carbon in the middle, that's a chiral carbon, and then just put the 4 groups onto it. It doesn't really matter how you put them. So I just give you an example. I will put the ethyl group here, and then you will attach to a OH group, and then you will have the methyl group and also the hydrogen group. Okay, so that's one possible way to arrange those 4 groups. And now we need to draw the enantiomer of this. So remember, if you want to find the enantiomer, you just need to switch any position of the 2 groups. Okay, so maybe I switch the position of the hydrogen and the methyl group here, then I will get the enantiomer. Okay, so remember, if we go through odd number of steps, we got the enantiomer. So this is an enantiomer of the original molecule. Okay, so any question for this one? Are you still with me? Okay, let's move on. Okay, so for this one, it have shown 5 different structure formula. Okay, and then we need to name for part A, what type of structural isomerism do P and R have? Take a look. P. Okay, for P, what's the functional group? You can see clearly a double bond here. And then take a look at molecule R. Again, the functional group, very clear, it's a double bond. And you can see the position of the double bond is different, okay? Hence, there should be position isomer, okay? And then, move on to part B. Which structure formula represent a compound that can exhibit cis-trans isomer? Okay, so in order to be cis-trans isomer, it needs to have identical atom or groups of atom on both sides of the double bond. Okay, so for those molecules have double bond, it should be P or R. Okay, now take a look. Do they have identical molecules on or groups of atoms on both sides? So for the first, as I'm pointing R, so we can take a look at R first. Okay, so for R, you can see the ending carbon is attached to 2 identical hydrogen. Okay, so the 2 hydrogen are attached to the same carbon. That means this alkene will not have any geometrical isomer. Okay, this one, not even E or Z. Okay, cis or trans. Okay, it would not form any geometrical isomer because they have 2 identical hydrogen attached to the same carbon. And then let's take a look whether P can form the cis and trans isomer. Okay, so for P, let's find the carbon on the double bond. And then, because for the carbon, for the left-hand carbon, it has one hydrogen attached to it. Right-hand carbon, also it has a hydrogen attached to it. Okay, so by putting the two identical hydrogen on different sides, we can have cis or trans isomer. Okay, so it should be the structure P that can have cis or trans isomer. Okay, and then for part C, which represent a pair of compounds that are non-superposable mirror image. Okay, non-superposable means it's chiral. Okay, if it's chiral, then we would be able to find a chiral carbon. Okay, and the system remind me I have less than a minute, so I will start a new meeting and let you to join. Okay. Okay, so I need to end the meeting and I will send you the code again.